This video is about interest rates. This is an application of exponentials, so our objective is to be able to solve interest rate problems. Let's first of all define our variables. P is in these problems are going to stand for principal, which is your initial amount. How much do you start with? R is going to equal the rate. This is the annual interest rate. So what are you getting for an annual interest rate? N is the number of periods. And then A stands for the amount after T years. Now, you might want to add down here then that T is the number of years that we do in this problem. So our formula for this is that A is going to equal the principal times 1 plus the interest rate for an annual interest rate divided by the number of years, or excuse me, number of periods. So like, for instance, if it's quarterly, that would be it's done 4 times a year. It's monthly, it's done 12 times a year. And then we put up in the exponent n times t. Because for instance, if you're doing it quarterly, that means 4 times a year. If you're gonna do it 5 times, 5 years, you're gonna have 5 times 4 gives you how many periods you do, you figure out interest. So this is the number of periods we calculate interest Remember that the 1 stands for, on this one, 1 stands for 100%. So that's why we're taking 1 plus the interest rate. This is the 100% is how much we start with the principal, and then we add interest on. So that's what the interest rate does for us. So this is our formula that we're going to use for these different problems. We can apply that to these different specific ones here. So if we do annual, then our n is going to equal 1. So when we put it into the formula, you get A equal to the principal times 1 plus the rate. Rate divided by 1 is just the rate, to the t power, because it will be t times 1 for that. So this will be the simplest one, is if you have it done annually. Semi-annual, if you put in 2 for n in both of these spots, you're going to have A equal to the principal times 1 plus the rate divided by 2. You don't get the whole rate every time. Since you're doing it every 6 months, you get half the rate each of the time. But then you compensate for that to get the number of periods, where you're going to do 2 times t up here to get to cover the fact that you're doing it twice a year. Then quarterly, that means n is equal to 4. So we're going to have the amount is going to equal the principal times 1 plus the rate divided by 4, and that's to the 4t power. And then lastly, when monthly will be when we have an n equal to 12 every month, so 12 months. So the amount will equal the principal times 1 plus the rate divided by 12, all to the 12t power. And this applies to any one of the different problems. Like if we said we're going to do it daily, then you'd use 365 as your n to do the problem. Let's do a couple examples here with these specific formulas. So first of all, this first one, we're going to invest $2,000 at 6% compounded monthly for 10 years. So we're going to put our formula as A equal to the principal, which is $2,000, times 1 plus the rate, which is in this case 6%. We don't put 6, we put 0.06 because we're taking off the percentage symbol and we're putting it into a decimal. And that's going to be divided by, here our n is going to equal 12 because it's monthly. So divided by 12, all to the 12 times 10 power because we have it for 10 years. All right, so we're going to put that into our calculator, calculate what that's equal to. So if we put in here 2,000 times, now here you could do this, you could think of this as 100%, so 1 point, and then whatever the decimal is for 0.06 divided by 12. So it is just one single base, but it's easy in these problems just to put 1 plus 0.06 divided by 12. And then we get that to the, and then we're gonna raise it to the 12 times 10 power. And since this raises it, the whole thing, I don't have to put parentheses, but if yours doesn't raise it, you need to make sure you put parentheses on the exponent. And that gives me $3,638 $3,638.79 for an answer. So there's what my amount turns out to be when I calculate this out. Now, just as a reminder, this base here, so I'm not going to do this every time, but when we do this base, 1 plus 0.06 divided by 12, the interest rate, or the amount you multiply by each time you calculate the interest, is 1.005. So this number here is 1.005. You don't have to put that in, you can just leave it in this original formula, but that reminds us that the general formula for an exponential is the initial amount times a base. This base is 1.005, and then raised to an exponent. Here our variable is number of years. We could change it to say 25 years. How much will it be then? So that's our exponential where the variable is in the exponent, in this case being time. All right, so for this one, it says compounded quarterly, so that will be an n equal to 4 for that quarterly. So I'm going to put amount equal to my initial amount, 5,000, times 1 plus 0.03, 3% compounded quarterly. I'm going to divide it by 4, and then take 4 times the number of years. That's my variable. The number of years is 20, and so I get that amount. Real quick on our calculator, let's go ahead and figure out what this base is. This 1 plus 0.03 divided by 4. So really the base is not just 1 plus this, it's 1.0075. That's what this represents, and you can change it to that, or I can just type in this whole expression into my calculator. So what I get is 5,000 times parentheses, I'm going to put 1 plus, I'm going to go ahead and leave it as this number here, 0.03 divided by 4, and then put it to the 4 times 20 power, which is 80. I'm just going to put it in the way it is. So you can do as much simplifying as you want to. This is going to be $9,090. 0.22 when I do that calculation. Again, if you wanted to, you could look at this and say, hey, this one, if we rewrote it to make it look more like an exponential, 1.0075, I could make this 5,000 times 1.0075 raised to the 80th power. See how 4 times 20 gives that to me. So this part here, okay, this can be rewritten here as a base to an exponent, and then I've got the initial amount here. Notice how fast that goes up. For 20 years, I've almost doubled my amount, and that's only at 3%. Notice on this one, for just 10 years, I'm getting close to doubling my amount because the interest rate is higher. All right, so the more we compound it, a basic concept here is the more we compound it, the faster your amount will grow. All right, so that leads us to an idea of what happens if we could do it all the time. Continuously is the word that we would use. Well, that prompts us to come up with a new number, a new irrational number. How pi, you know how pi is an irrational number. That's a decimal that goes on forever and never ends and never repeats. Well, compounding continuously, if we were to take that, instead of doing it daily, we'd do it every minute, every second, and we kept doing it more and more often. If we did it an infinite number of times, compounded continuously, it would produce a new number, which is called Euler's number. Euler's number, we usually use a little e in script form, and e itself is approximately equal to 2.71828, and then it keeps going on forever. So this number will become a new number that we'll be dealing with here as an application of interest rate, and then we'll start using it in other areas. It has its applications in other areas. Remember that this is an irrational number. It never repeats or terminates. Never repeats, never terminates, never ends. Okay, that's an important number, and it comes from these interest rate problems. That's where it's developed. Now, where you'll find it on your calculators, if you look at your calculator, you'll find it in two places. You'll find the E just above the division symbol here. Okay, so it's on that side of the calculator. If you want to do e to the x, notice it's just above this ln right here. So if I were to do second and then e to the x, notice it puts that e there. Now we're to put it to the first power. There I get my 2.71828, etc. And it would keep going forever and never repeat. So those are the two places to find it. Here, we don't use this one very often, but here, this e to the x we'll use very often to do exponentials with this. All right, so for our continuously, interest compounded continuously, this is if it's compounded all the time, so like an infinite number of times per year, then we're going to use this new formula. So this is the amount that we have is the principal, that's all the same, but instead of the 1 plus r, you end up getting this e, and the interest rate goes up into the exponent, r times t power on this, where t is time in years. And so this is a strong formula. This is the way that we could earn the most interest rate, say on our savings, things like that. This is the compounded continuously formula. All right, so let's go down here and do a couple examples. So if I want to find out the amount of $500 invested at 7% compounded continuously for 8 years, I do amount equal to my principal times e to the, I'm going to put the rate, 0.07, it goes up in the exponent for this, times 8 power. Let's go ahead and calculate that. So if we do that on our calculator, we get 500, okay, times e is our base in the exponential, so e to the x, and then 0.07 times 8. And what we get for that amount is we get $875.34. So when we round it, so 875.34. So again, that's a good amount of interest you get in 8 years, that because we compounded continuously and we've got a high interest rate of 7%, that will add up quickly. All right, let's do this last one here. $5,000 at 3%. We're going to put e to the 0.03 times 20. And what we get for that when we multiply that through, let's go ahead and check that out. All right, so we're going to notice that this one's like the one above. So when we did number 2 above, that was 3% compounded quarterly for 20 years. Is this one going to be more or less? Well, we do it more often, so this should be more. So we're going to go ahead and calculate that. We get 5,000 times e to raised to the 0.03 times 20, and we get $9,110.59. So notice if we do it continuously, faster and faster and faster, notice that we get more money than we do if we compound it quarterly. Because you compound more often, it gives you more interest. So these are applications of exponentials, specifically interest rate problems. In the future, we'll look at what happens when we depreciate problems, and also we'll look at other types of problems that might involve exponential growth or decay as an application.